Welcome back, and today we're going to be doing a lot of proofs by mathematical induction. So our first one is proving that 3 to the power of 2n minus 1 is divisible by 8 for all n being greater than or equal to 1. So the first step in our mathematical induction is our base case. And this base case is going to be when n is equal to 1. So when n is equal to 1, we have 3 times to the power of 2 times 1 minus 1, which becomes 3 squared minus 1, which becomes 9 minus 1, which is 8. And obviously 8 is divisible by 8, so the base case holds. And now we're going to have our second step, which is the inductive step, which is the step where we're going to assume. So we're going to assume for some k being greater than or equal to 1, we're going to have 3 to the power of 2k minus 1 is divisible by 8. And we're going to have an integer m such that 3 to the power of 2k minus 1 is equal to 8m, because it's just because 8 multiplied by m still means that that number is going to be divisible by 8. And now that we made this assumption, we can move to step 3, where we have to show for k plus 1. So this is going to be showing that 3 to the power of 2 times k plus 1 minus 1 is divisible by 8. So we're going to try to set this up. So we're going to get 3 to the power of 2k plus 1 minus 1 is going to be equal to, if you factor in the 2, 3 to the power of 2k plus 2 minus 1. And if you split up the exponents, this becomes 3 squared multiplied by 3 to the 2k minus 1, which gives us 9 times 3 to the 2k minus 1. However, if we look at our assumption from part 2, we're assuming that for some k, 3 to the 2k minus 1 is divisible by 8. So by using the hypothesis, we get 9 times 3 to the 2k minus 1 is equal to 9 times 3 to the 2k minus 9 plus 8, which equals to 9 times 3 to the 2k minus 1 plus 8. And by the hypothesis, we're saying that 3 to the 2k minus 1 is equal to 8m, like what we had here, which means that we're going to get 9 multiplied by 8m plus 8 is equal to 8 multiplied by 9m plus 1, if we factored out an m. And since we can see right here that it's going to be a multiple of 8, because 8 times 9m plus 1, anything is going to be multiplied by 8. This means that 3 to the 2 multiplied by k plus 1 is a multiple of 8. And since we're doing by mathematical induction, if our base case works and when k plus 1 works, we can say that for the whole expression it works. So next up we have prove that n factorial is greater than 2 to the power of n for all n being greater than or equal to 4. So we're going to have our step 1 again, which is going to be our base case. However, this base case isn't when n is equal to 1. This is going to be when n is equal to 4. So we're going to have 4 factorial, which is 24, and we're going to have 2 to the power of 4, which is 16. We can see that 24 is greater than 16, so our base case holds. And now we're going to use our inductive step. So we're going to assume for some k being greater than or equal to 4, we will have k factorial greater than 2 to the k. But now we want to prove the statement for k plus 1. So we know that we have to prove that k plus 1 factorial is greater than 2 to the k plus 1. So starting from the left side, k plus 1 factorial we can break down into k plus 1 multiplied by k factorial. But now we know from the hypothesis that k factorial is greater than 2 to the power of k. So multiplying both sides by the positive k plus 1 will preserve the inequality and will become k plus 1 factorial is equal to k plus 1 multiplied by k factorial. That doesn't change. But now we're going to have this greater than k plus 1 multiplied by 2 to the power of k. So we've reduced the problem to comparing just k plus 1 multiplied by 2k, which is right here, with 2 to the k plus 1. So now what we're able to do is we're going to have 2 to the k plus 1 is just equal to 2 times 2 to the power of k. So we'll draw an arrow up top because we want to show that now k plus 1 multiplied by 2 to the power of k is greater than 2 times 2 to the power of k. And since 2 to the power of k is greater than 0, this is equivalent to 2 k plus 1 is greater than 2. And if we look at our original question, it's for n is greater than or equal to 4. So this is going to be for when k is greater than or equal to 4. And we can see that that would always be true, which means that our k plus 1 factorial is greater than our k plus 1 multiplied by 2 to the k, but that is greater than 2 to the k plus 1. And since this is true, because now we have k plus 1 factorial is greater than 2 to the k plus 1, and the base case is true, we know that is true for the entire question. Now we have question 3, where we have 5 to the power of 2n minus 2 to the power of 5n is divisible by 7 for n being greater than or equal to 1. So we're going to start off with our base case. And our base case is back to when n is equal to 1. So this becomes 5 to the power of 2 times 1 minus 2 to the power of 5 times 1, which becomes 25 minus 32, which is negative 7. And since negative 7 is divisible by 7, the base case holds. Now we're going to have our inductive step. So for some k, it's going to be 5 to the power of 2k minus 2 to the power of 5k is divisible by 7. And that's going to be our assumption. And since it's divisible by 7, that means any multiple of 7. So it's going to be 5 to the 2k minus 2 to the 5k, can just say is equal to 7m to make it a proper equation. But now we want to move on to step 3, which is our proof. So we want to prove that 5 to the power of 2 times k plus 1 minus 2 to the power of 5 times k plus 1 is divisible by 7. So we can start off by expanding this. So we get 5 to the power of 2k plus 2 minus 2 to the power of 5k plus 5. And this just becomes equal to 5 squared multiplied by 5 to the 2k minus 2 to the 5 times 2 to the 5k, which gives us 25 times 5 to the 2k minus 32 times 2 to the 5k. And we want to bring in the expression 5 to the 2k minus 2 to the 5k from our hypothesis. So we add and subtract the same term. So I'll bring an arrow up again so we don't run out of space. And we'll get 25 times 5 to the 2k minus 32 times 2 to the 5k is equal to 25 multiplied by 5 to the 2k minus 25 times 2 to the 5k plus 25 times 2 to the 5k minus 32 times 2 to the 5k. And what this does is it allows us to factor out our 25 so that we get 5 to the 2k minus 2 to the 5k plus 25 minus 32 times 2 to the 5k, which simplifies to 25 times 5 to the 2k minus 2 to the 5k plus, this is going to be negative 7 times 2 to the 5k. However, if you remember from our assumption, we have 5 to the 2k minus 2 to the 5k is 7m. So this is going to become 25 multiplied by 7m, and then this is minus 7 times 2 to the 5k. But one thing you can notice is both terms here have a 7. So we can factor out the 7, which leaving us with 25m minus 2 to the 5k. However, the whole expression, because of the 7, is a multiple of 7. So this shows that when it's k plus 1, it's still a multiple of 7, so it's divisible by 7. And we know that the base case is divisible by 7, so this means that our entire expression is true. So now for question 4, we have 2 to the power of n is greater than n squared, for n being greater than or equal to 5. So we're going to start off with our normal base case. So this is going to be when n is equal to 5. So for our base case, we have 2 to the power of 5, which is 32, and we have 5 squared, which is 25. And since 32 is greater than 25, we can see that our base case is true. So now we're going to make our assumption that 2k is k squared, is greater than k squared. And we're going to assume this for some k that's greater than or equal to 5. And now we're going to prove it for when 2 to the power of k plus 1 is greater than k plus 1 squared. However, 2 to the power of k plus 1 is equal to 2 times 2 to the power of k. But since using the hypothesis, if we have 2 times 2 to the power of k, we can just set this greater than 2 times k squared, since it's just our hypothesis with a multiplied by 2 on each side. So now it's enough to show that 2k squared is greater than or equal to k plus 1 squared. Now the reason that this is important is because if we prove this inequality, then we have 2 to the k plus 1, which is greater than our 2 to the k squared, which we'll have as greater than or equal to k plus 1 squared. And if this gets proven, this solves our original of 2 to the k plus 1 being greater than k plus 1 squared, which is what we want. So now drawing an arrow up, 2k squared, and if we subtract k plus 1 squared is equal to 2k squared minus k squared plus 2k plus 1, which is equal to k squared minus 2k minus 1. So now, because this comes from the inequality, we want for k squared minus 2k minus 1 is greater than or equal to 0. However, for when k is greater than or equal to 5 from our hypothesis, this is true. So this means that our 2 to the k plus 1 is greater than our k plus 1 squared. And this means that 2 to the k plus 1, since it is greater than 2 times k squared, and this is greater than k plus 1 squared, we're able to see that this is true for when it's k plus 1 and the base case, so the whole identity holds. So now we have 1 cubed plus 2 cubed all the way up to n cubed being equal to n squared times n plus 1 squared all divided by 4 for when n is greater than or equal to 1. So the first thing we're going to look at is our base case. And this is when n is equal to 1. So for the left hand side, this is 1 cubed is equal to 1, and the right hand side is going to be 1 squared times 1 plus 1 squared all divided by 4, which will give us 1 times 4 over 4, which equals 1. So the base case holds. Now we're going to assume that for some k being greater than or equal to 1, it holds where 1 cubed plus 2 cubed all the way up to k cubed is equal to k squared times k plus 1 squared all divided by 4. And we want to prove where 1 cubed plus 2 cubed all the way up to k cubed plus, this time we're going to have k plus 1 cubed is equal to k plus 1 squared times k plus 2 squared all divided by 4. So for the left hand side, we have 1 cubed plus 2 cubed plus all the way up to k cubed plus k plus 1 cubed. However, if we look at our hypothesis, we are able to replace our 1 all the way up to k with k squared times k plus 1 squared divided by 4. And now we just add our extra portion of k plus 1 cubed. So now bringing this over here, we're going to have an expression involving k and k plus 1 only. So by doing this, we're going to factor out k plus 1 squared. So this gives us k plus 1 squared multiplied by, this is just going to be k squared over 4 plus k plus 1. And then simplifying the inside will give us k plus 1 squared all multiplied by, after you simplify, is going to become k squared over 4 plus 4 times k plus 1 over 4 which will give us k plus 1 squared multiplied by k plus 2 squared all divided by 4. However, if we multiply in our k plus 1 squared, we'll see that this becomes equal to k plus 1 squared times k plus 2 squared all divided by 4, which matches our desired formula for n being equal to k plus 1. So since it works for k plus 1 and the base case, we can say that this works for the whole thing. Now we have our final question where it's 1 squared plus 3 squared all the way up to 2n minus 1 all squared is equal to n times 2n minus 1 times 2n plus 1 divided by 3. So our first thing is our base case. So this is going to be for when n is greater than or equal to 1. So our left-hand side base case is going to be 1 squared equaling 1, and our right-hand side is going to be 1 times 2 times 1 minus 1 times 2 times 1 plus 1 all divided by 3, which will equal 1. So the base case holds. Now we have our inductive step, which is our hypothesis. So we assume for some fixed k being greater than or equal to 1, we're going to have 1 squared plus 3 squared plus 5 squared all the way up to 2k minus 1 squared is going to equal to k times 2k minus 1 times 2k plus 1 all divided by 3. And we want to prove this large equation of 1 squared plus 3 squared plus all the way up to 2k minus 1 squared plus 2 times 2k plus 1 minus 1 squared is equal to k plus 1 times 2 times k plus 1 minus 1 times 2 times k plus 1 all divided by 3. So the first thing that we can do is 2 times k plus 1 minus 1 is going to be equal to just 2k plus 1, and 2k plus 1 is just going to be equal to 2k plus 3, which helps out a lot. So starting from the left-hand side now, again, just like normal induction, we're able to kind of just separate our last little chunk and look at our starting piece, because that is normally what is equal to our hypothesis. So this becomes k times 2k minus 1 times 2k plus 1 divided by 3, and now it's just plus 2 times k plus 1 minus 1 squared, which is a lot easier to work with. And just like normal, we're able to find something to factor out. So here we're able to factor out a 2k plus 1, which will leave us with k times 2k minus 1 divided by 3 plus 2k plus 1, all in the end bracket. And now we want to simplify what's inside the bracket. So simplifying inside the bracket, we'll get our 2k plus 1 on the outside, and this will become k times 2k minus 1 divided by 3 plus, and now we're going to multiply both top and bottom by 3 for common denominators. So it's 2 times 2k plus 1 divided by 3. Now adding these together, we get where it becomes 2k plus 1 multiplied by 2k squared plus 5k plus 3 all divided by 3. Now factoring this, we have 2k plus 1 times 2k squared plus 5k plus 3 divided by 3, and this is going to be equal to, once you factor, it's going to be 2k plus 1 multiplied by 2k plus 3 times k plus 1. Which, once you simplify a little bit more, by just putting in our 2k plus 1, this gives us k plus 1 times 2k plus 1 multiplied by 2k plus 3, all divided by 3. Now, if we go back, we'll notice that if we simplify the right side a little bit more, this actually just becomes k plus 1 times 2k plus 1 times 2k plus 3, all divided by 3. Which means that our k plus 1 matches and our base case matches, meaning that the whole equation is equal.